Hi all. Today's video we will discuss about the tree data structure. I think already everyone know it is a very important data structure and we want to take a discussion in this video. So we can get started. For a tree data structure we need to know some of the concept regarding the tree data structure. For example, what is the root, key, edges, siblings, parent, child node, leaf node, the height of the tree, etc. So the root of the tree means we already know the first element where we need to start from the tree. So that is the, here you can see the P is the root of the tree. And the value inside that node is called key value. And the edge means connecting to the one node to another node, that is called edge. And the siblings means if a node has two child nodes. For example, Q is a parent node. We can call as Q as a parent node. The edges connected to other two nodes is A and B. So we can say that A and B are the siblings of Q. Then the leaf node. This is, for example, you can see here this tree. For example, this is the all tree, but this L, E, F, G is a subtree of P. We can see that the subtree, this is a subtree of the main tree because the tree has some kind of like this also like a tree and but it is a part of the previous one. The P, for example, P is the total subtree name as P. For example, this is the leader, then we can see that it is the part of this tree. So that means the subtree of this one. And we can see that the here L is the parent. Okay. And the E, F, G are the children node. So and one more thing, the leaf node. Leaf node means the ending nodes are the leaf node. Because there is no further child node from that particular node, then we can say that the leaf node. And the last, the height of the tree. It is very important. The height of the tree means the distance from the first node, the root node to the leaf node is called the height of the tree. Means how many trees are there. Means how many nodes are need to cover once we end in the leaf node. For example, you can see that the longest path means P to R. This is one path. C to R to C. This is another part. C to M and M to H or M to I. So this path will be the height of the tree. I will tell you one more time. PRCMI. This is the one height of the tree. And PRCMH. So this is the height of another tree. So these are the main concept regarding the data structure, tree data structure. And we can divide the tree data structure into different categories, but all we don't want to need, but we definitely want to give some understanding regarding the tree concept. That's it. So first one we can see general tree, binary tree, binary search tree. So category of binary tree, binary search tree, ABL tree, red black tree, splay tree, tree, and B tree. So I just want to know you must focus about the general tree, binary search tree, BST. It is very important. So we need to more focus on these videos, these kind of trees. And first we can, I will tell you, just want to, these are the things. First one is general tree. A general tree is a data structure where are no constraint or the hierarchical because we are ordering as a hierarchical order. We are connecting the data as a hierarchical order. Properties. Node can not have any number of children. For example, P as a root node, it has any number of children, but in the coming session, we already discussed it has two children, three children, so that kind of thing. But in the general tree, there is no restriction. A node can, for example, P has this is a child node, this is a child node, and you can add one more child node. There is no issue for the general tree. Usage used for to the hierarchical data such as folder structure. For example, folder structures. Just general tree means folder structure in the PC. So that is the best example. And the binary tree. Binary tree, you can same as the name. You can see that the one node contains only two child node. That is the very important concept. The binary tree data structure is the following properties can be found. the follow as the properties of it follow the same properties of tree structure, but it not have at most. That means the most two children, two children for from the root. So that is the one condition. It's a very important condition. So yes, and not can have bold also. Okay, yes, bold. Yeah. So a knot can have at most two children knot. And there is these two children knots are known as left child and right child. That is very important. Left child and right child. So yes, left and right child. It is very important. For example, like you can see here, P is the root knot, Q and R. So this is left child. This is right child. For example, here you can see that at most two children. Okay, at most there is no nothing. There is a possibility if a root has no children, one children and two children. So that is the possibility. The knot can at most two children. So that is the one condition. Usage used to by the compilers to build a syntax tree. That is very important. Used to implement the expression parsers in the expression solvers. Used to store the router table in router. So these are the main usage of the binary tree. Then the third category is the binary search tree. So the binary search tree is more constructed extension of the binary tree. Okay, binary tree. So the following properties of the binary tree has a unique property known as binary search tree property. This property states that the value of the key, which is very important. We already know the binary tree has only at most two children we can implement. But in the case of binary search tree, there is a condition. The right child always greater than the left child. For example, you can see here 56. This left child always less than the root node, and this right child always greater than the root node. That means there is an order in the binary search tree. This has a unique property is known as, which is very important. The unique property is known as binary search tree property. This property states that the value of a key in the left child of a given node should be less than or equal to the parent. Should be, okay. Should be equal to the parent value, and the value of the right child should be greater than or equal to the parent value. It is very important. This concept. So left value, for example, we can consider this one. Left value less than or equal to not value, this one greater than or equal to right value. Because here 65. 65 is greater than 63. That means greater than our condition satisfied. 65 is less than 67. So the all category satisfied. That means it is a BST. Usage means used to implement simple sorting algorithms. So because we have a sort, we already know there is a pattern. If the left item is less than, right item is more valuable, means more value. So we can check. For example, if I given in sorting, you're given an data and you say that you need, I want to do it in a correct position. Then I can check with the root node. First, I check with the root node. When the value is greater than root node, I will go to the right. If the value is less than the root node, then I will go to the right side, because at the same point of time we can divide the one portion. Okay, we can avoid the one portion of the system. That means that much of time we need to consume. So this is very important. In the simple sorting algorithm, it is used, can be used in the priority queue. It is also very important, used in many search applications where the data are constantly entering and leaving. And able tree. For the data engineering part, it's not important. We want to just go through it. What are the things? An avial tree is a self-balancing binary search tree. This is the first tree introduced which automatically balance its height. Okay. As the property of the binary search tree self-balancing, each node store the values called balance factor, because once we took the all idea regarding this balance factor, we will get 0, because there is one more item, 0, -1, 1. So we can say that the total count of the system will be 0. So that is the all idea balancing factor. Each node store a value balance factor, which is the difference in height between the left subtree and the right subtree. Okay. So at the overall, it will be like, for example, you can see here 56, 30. Here you can see it is balanced. This node is 22 is balanced, 22, 11, 11. So this is 0. But here you can see that there is only one node, right? Only one node, then it will be like as -1. But here we can see that the right tree is balanced here, but the left tree is 1. There is no balancing. Then what we can do, we can put as 1 here. Hmm. Then the overall one, this -1, this one will be cancelled. So that means the overall this tree is a balanced one. Used in situations where frequent insertions are involved. So this is very important. Frequent insertions are involved. Used in memory management subsystem of the Linux kernel to search the memory region and process during the preemption. So that is very important. Then next one is fifth one is red black tree. The red black tree is a self-balancing binary search tree where each node has a color, red and black. The colors of the node is used to make sure that the tree remains approximately balanced during the insertion and deletion. Properties. The follows the binary search tree, the properties of binary search tree BST, self-balancing. Each node is either red or black. Root is black, sometimes emitted. All leaves denoted as null as black. If nodes are red and both the children are black, every path from the given node and leaf node must be go through the same number of leaf node. For example, you can see the root node black. This is the one, and the ending is nil. Means null. There's no nothing, right? So that kind of thing we are some kind of predefined instruction for the red black tree. Usage. The base of the data structure is used in the computational geometrical. Used in the completely fair scheduler used in the current Linux kernel. Used in the Apple system called implementation of Linux kernel. That's it. Then splay tree. The splay tree is also a self-balancing binary search. It is also a kind of variation. Follow the properties of binary tree, self-balancing, recently accessed elements are quick to access again. Recently accessed, this is very important. Recently accessed elements have quick access again. So that kind of situation we can use. Okay, for example, if you have an application, you want to need the users list. Okay, you want to you want to, for example, you are a business owner, data owner, you want to access the data of the user who enter a system recently because, for example, you have a resort or like that, and some users are really keen to interest and visit your resort. So they are frequently checking your website and price and all, right? So that time we can get, if for a more number of time or recently they visited, we can get the contact, we can call it, because if we give a push to them, we will get a good outcome from them, right? So that kind of situation we can use this tree structure. And um, for example, you can insert search for this one, search. After performing search, insertion, or deletion, splay tree perform an action called splaying, where the tree is rearranged by using the rotation. And the particular element is placed in the root of the tree. For example, splay tree and search 28, then it will be moved into the 28 here, right? So there will be a rearrangement happen, then we can easily kick out the element. So every time we are searching, it is totally rearranging and placed in the correct node. So that is the main advantage used to implement the cache, the garbage collectors and data compression. Tree is named as tree plus heap. That is the seventh data structure binary search tree. Each node has two values, key and priority. Okay, heap, tree plus heap. That is tree. The key follows the binary search tree for a property, and the heap means the priority. For example, you can see here we can add 100. This is the value, right? For the tree, this is the value. M is the priority. So depend upon the priority, we can sort it out. Used to maintain authorized certificate in public key crypto system. This is very important. Hashing. Hashing plus tree maintain. Used to perform the first set of operation. Then next eighth one is B tree. The B tree is a self-balancing search tree and contain multiple nodes which keep data in sorted order. Each node has two or more children and consists of multiple keys. Properties: every node X has the following keys. For example, the n number of keys and keys stored in an ascending order. Leaf, where X is a leaf or not, and there is a children, that kind of thing. The balancing factor also there. For example, root, internal root, leaf node, everything as a rearrange in a B tree. But we are not very important, but just want to analyze it, just want to go through it. Used in the database indexing to speed up the search, and used in file system to implement the directories. So these are the things. And so I think we almost cover the main part of the tree structure. And we are coming to the traversal. I think you can not clear this one. I will show in a gray. Okay, yeah. For the tree traversal, we already know it is divided into two: the breadth first and depth first. Breadth first means it is arranging like that. Mm, okay, yeah. Breadth first means one by one. For example, this is the, for example, this one. So first I arrange first order, next one. This is the breadth first arrangement. Okay. Depth first means we have some kind of order: pre-order, post-order, and in order. So these are the things. Depth first. So the in order traversal means if we are given a tree, first we analyze the left part of the root, left part of the tree, then coming to root, then right. So that is the order, and that is in order. Pre-order means we are starting from the root, left, right. Post-order means left, right, then root. So this is the order. Okay, I'm already writing here this one. So you can, in order means left row, left part first, then root, then right. Pre-order means root first, then left, right. Post order means left, right, root. So these are the order, traversal of order. And so this is very important. And we can, I think you will get a better understanding about this one. Then we can move on some of the questions part. So I will share my screen here. Yes. Okay. So the binary tree in Python means a class node. Okay. We are normally, how we create a node? Normally we have a node. We are creating a class node. This is the constructor we are doing. Here we are implementing self dot left, self dot left equal to none, self dot right equal to none, and the key value, self dot key equal to k. So these are the things. And here root equal to node of 10. Root equal to node of 10. If we are calling, it will be calling to here and create a node. And root dot left node of 20 means they are creating at the left side one node, and the right side here it is creating another node in the right side, root right side. Then the root dot right, that means root right, then right, there is a node. So these are the construction of the binary tree in Python. Then next one is in order implementation. How the in order implementation is possible. In order means I already told you. Um, first we do left, root, then right. So that are the combination. So here we already like constructing root equal to node of 10, root dot left equal to node of 20, root dot left right equal to node of 30. So we are creating this one and we calling this function. What we call, if the root not equal to none, root not equal to none, that is our condition, root not equal to none. Otherwise, we will do in order of root dot left, we are calling the leftmost function. We are passing it root dot left, and until it is root not equal to none, it will be work and find the last node. Then print the root dot key. Then what we do, we are checking there is any right part on that. That is in order root dot right. So it will check here, then come back, then do it. So that is the function we are calling. So we will get 20, 10, 40, 30, 50. For example, I will tell you, I will write here paint. Okay, so you can see here, node. First node is 10. So I am writing node here 10. So I am writing one here and then 10. Okay, first node I write 10. Then what is the next? Node of 20 left. Node of 20. That means I am creating one more thing here, 20. 20. Then the next one I'm writing to here. You can see here, no root dot right equal to 30. So that I'm writing here 30. 30. Then the next one is right dot left is 40, right dot right is 50. So I need to write two things, right, left and right. So I'm writing one here. I'm writing one more here. This is 40. Then this is 50. Okay, you better clarity, right? Then the first one is we need to check. First one is in the from our this condition. It is very important. I will paste from here. Okay. First one is we need to check the root not equal to none. For example, here it will be coming to here, coming to here, coming to here. Then what will do? Coming to here, it will be check if the root not equal to none. Then in order root dot left. So root is not none. Then it will come to in order of. Then it is calling again to the this one 20. Then what it do? Then again it calling to this one and it will check here. It will be root. Then again it will be calling the root is none. Here also none. Then what we do? It will be print the 20. Then in order of root right, it will check the root right. There is no item, right? Yes, 20. Then it back to this one. Then in order of this already printed. Then come to here. In order means left, root, right. Then 20, 10 is printing. Then it will be come to here 30. Then it will be passing to in order of left. The left of this one means 40. So it will be 40. Then there is no item here and here. Then it will be back to here. Then 30 will be writing here 30. Then 50. So that is the order we get here. 20, 10, 40, 30, 50. So that is the in order traversal. I think you will get the better idea regarding the in order traversal. Then we need to discuss about the pre-order traversal. So here all time complexity is big O of n, and the space complexity means it will take some space to storing these kind of recursion call. That means big O of h. And the pre-order traversal, we already know the same thing. Pre-order means pre-order. Pre-order means first it will be checking the route, left, right. So there is an order arrangement. First we print the route node, then route of left, route of right. So that kind of thing here we are talking about pre-order. So the pre-order means when we checking here, first we will print 10, 10, then the right, left, in the left 20, then it will back to the here, then it will be printing 30, then 40, then 50. So that is the order. 20, 10, I will 10. The root node is 10, 20, 20, 30, 40, 50. So this is the order in the pre-order. The time complexity is big O of n and space complexity is big O of h. Then the post order means post order. Yes. Post order is also very important. Post order means first it will be checking to the left side, then go back to the right side, then row. That is the order. So first post order of root dot left. Then if here you can see the post order of left, then it picking, then post order of right, then printing. Okay, printing the root of key. So this is the order of the post order. The same thing as we already discussed. Time complexity is bigger of n and the space complexity is bigger of x. Yes, I think then very important thing is height of the binary tree. It is very important. Height of the binary tree. Height of the binary tree, how we can find? So we already have a given list of tree, right? Then first we check if the height of the tree, there is no item. We can say that there is nothing in the height, we can return the 0. But if the height is there, what we do, LH equal to height of the root of left. We are calling it root of left and root of right and finding the maximum. Every time we are finding the maximum, then plus 1 means root. That is the first set. Then we check each and every node, then return it. So that is the maximum value of the height in the root. So this is the iterative solution. For example, if we want to reduce the code, we can say that here you can see that root equal to none, we can return the 0. Otherwise, height of root, the same call is root of left, the maximum of root of left, comma, height of the root of height plus 1. This is the one we are using in the using the recursive call. Okay, recursive call we are using the 3 is the height of the tree. So this is very important. You can definitely want to check this one. And one more thing I just want to check with you. Yes. Yeah. I think hope you all clear. If you have any doubt, just comment below. Okay.